Hello my student, we're gonna start a new chapter which is chapter 7, DC Machinery Fundamentals. DC machines are generators that convert mechanical energy to DC electrical energy and motors that convert DC electrical energy to mechanical energy. Most DC machines are like AC machines in that they have AC voltages and currents within them. DC machines have a DC output only because a mechanism exists that converts the internal AC voltages to DC voltages at their terminals. Since this mechanism is called a commutator, DC machinery is also known as a commutating machinery. So we are using commutator to convert AC to DC. This is DC. Section 7.1. A simple rotating loop between curved pole faces. The simplest possible rotating DC machine is shown in figure 7.1. This is a simple machine. Consists of what? Two poles here, north and south, and we have a loop here between the poles, which rotates between the poles. It consists of a single loop of wire rotating about a fixed axis. The rotating part of this machine is called what? The rotor, and the stationary part is called what? Stator. So we have a rotor and stator. The voltage induced in a rotating loop. If the rotor of this machine is rotated, a voltage will be induced in the wire loop. In the wire loop, to determine the total voltage E total on the loop, examine each segment of the loop separately and sum all the resulting voltages. Then we can get what? E total. So the voltage on each segment is given by the equations. E induced equal what? VBL. Velocity multiply magnetic field multiply length of the loop or conductor. So we have to examine each segment 1, 2, 3, and we can get what? The voltage at each segment. For segment 1, EEBA, VBL positive into the page under the pole faces. And for the second segment BE, so ECB will be what? 0. Okay, so segment 3, okay, we have maximum positive out of the page. Then the fourth segment, which is EAD, it will be 0. So if we add all the voltages at each segment, we can get what? This equations, which is here E induced equal what? 2 VBL under the pole faces, because beyond the pole edge we don't have voltage. It will be what? 0. Okay, it will be here 0. There is an alternative way to express equation 7.5, which clearly relates the behavior of the single loop to the behavior of a larger DC machine equal what? VR radius or multiply what? Omega. Okay, we can write this equation also here. E induced is equal to 2 over pi omega multiply flux. Let's move to the next slides. Thus, the voltage generated in the machine is equal to the product of the flux inside the machine and the speed of rotation of the machine multiplied by a constant representing the mechanical construction of the machine. In general, the voltage in any real machine will depend on the same three factors. We have three factors: the flux in the machine, the speed of rotation, and what? A constant representing the construction of the machine. Getting DC voltage out of the rotating loop. Here, two semicircular conducting segments are added to the end of the loop, and two fixed contacts are set up at an angle such that at the instant when the voltage in the loop is 0, the contacts short-circuited the two segments. In this fashion, every time the voltage of the loop is switch direction, the contacts also switch connections, and the output of the contacts is always built up in the same way. This connection switching process is known as a commutation. As a what here? Commutations. The rotating semicircular segments are called what? Commutator segment, and the fixed contacts are called what? Brushes. So we have commutator and brushes. This is the figure, guys. We are shifting the negative sign to what? To be what? Positive. For AC, we will have a sine wave. Okay, sine wave. Positive and negative. But now we are shifting the negative to be what? To be what? In positive sides. So we are getting what? Trying to get what? DC, direct current, which is it here. It will be what? Straight line. If we increase number of loops, we will get what? At the end, straight line. DC what? Output. By using what, guys? By using here commutator and what? And brushes. Okay, we have commutator and brushes. Let's move now to the next slides. The induced torque in the rotating loop. Now we'll write an equation to what? Calculate the torque. The approach to take in determining the torque on the loop is to look at the one segment of the loop at a time, and then sum the effects of all the individual segments. We will use these equations. F equal what? ILB. Okay, as you can see here, we will sum all the torques, okay, at the segments. Then we can what? Write this is the equation here. Torque induced equal what? To RILB. Or we can rewrite these equations to be what here? Torque induced will be 2 over pi flux multiply current. Okay, if we substitute for the flux here, and this is for area, okay, we will get this another equation. Thus, the torque produced in the machine is the product of the flux in the machine and the current in the machine times same quantity representing the mechanical construction of the machine. The percentage of the rotor convert by pull faces. In general, the torque in any real machine will depend on the same three factors. What are they? The flux in the machine, the current in the machine, and a constant representing the construction of the machine. Now let's move to the next slide. We have example 7.1. Example 7.1. Figure 7.6 shows a simple rotating loop between curved pole faces connected to a battery and resistors through a switch. The resistors shown models the total resistance of the battery and the wire in the machine. The physical dimensions and characteristics of this machine are: radius we have here 0.5 meter. We have resistance 0.3, battery 120 volt, length 1 meter, B, which is here magnetic field, Tesla 0.25. Okay, this is the information given. Okay, so A, what happens when the switch is closed? Then B, what is the machine's maximum starting current? What is the steady state angular velocity at no load? We'll try to solve this example now step by step. I will open a new page. Now we'll try to solve example 7.1 part by part. For A, when the switch is closed, okay, so here a current will follow in the loop. Since the loop is initially stationary, so E induced will be what? Will be at when closed here, E induced will equal here 0. Therefore, the current will be given by here I equal what? I equal VB minus E induced. This is what here? Ohm's law. Voltage over what? Resistors. Okay. So we will have, because E induced is 0, so VB over R only. The current flows through the rotor loop, producing a torque. Also we have a torque. Torque induced will equal what? 2 by 2 over by flux multiply current. Okay, so this induced torque produces an angular acceleration in a counterclockwise direction, so the rotor of the machine begins to run. Okay, now B, okay, so what is the machine's maximum starting current? What is its steady state angular velocity? Okay, at starting conditions, so I will equal what? VB over R. We have the battery voltage 120 over what? Resistance 0.3. The answer will be what? 400 ampere. Maximum what? Maximum current at starting. Now at no load steady state conditions, the induced torque must be what? Must be 0. Okay, torque induced will be what? 0. Okay, So here the fact that I will be what? Also 0 ampere means that the battery voltage VB equal what? Equal E induced. Therefore the speed of the rotor, we can write now this equations. V battery equal what? E induced equal 2 over by flux omega. Okay, now we need omega, so we have to rewrite these equations here. So omega equal what? VB over what? 2 over pi multiply what? Flux. Okay, which is equal here VB. We can remove this value here and use this one. 2 omega equal what? 2 VB over 2 R L B. Okay, now substitute the values here. 120 and then 2 multiply 0.5 multiply 1 multiply 0.25 for Tesla. The answer would be omega here will equal what? 480 rad per what? Per second. Okay, this is for B. Okay, now let's move to part C. Part C. Suppose a load is attached to the loop and the resulting load torque is 10 Newton. What with the new steady state speed B? How much power is supplied to the shaft of the machine? How much power is being supplied by the battery? Is this machine a motor or generator? Okay, now C. We know that at a steady state, okay, torque load will equal what? Torque induced. Okay, which is equal here 2 over pi flux current. Therefore we have here current will equal what? Torque induced over what? 2 over pi multiply flux. We can also here change this quantity to be what here? Torque induced over what? 2 RLB. Okay, substitute the value now. We have torque induced, it is given here 10 Newton over 2 multiply 0.5 multiply length 1 multiply 0.25 for Tesla. So the answer will be how much here? Will be 40 ampere. This is the answer. So by Kirchhoff voltage law, okay, we have E induced is equal what? 120 volt minus what? Minus 40 multiply 0.3. This is V battery minus what here? IR. Okay, current multiply resistor. So the answer will be 10108 volt. Okay, so finally the speed will be what here? Omega will equal what? E induced over what? 2 to RLB. Okay, substitute the value here. 108 E induced, we just calculated, over 2 multiply 0.5 multiply 1 multiply 0.25 for Tesla. The answer will be 432 rad per second. Now we can calculate the power supplied to the shaft. Okay, the power now will be P will equal what? Torque multiply angular speed. 10 multiply 432. We just calculate this value. So the answer will be what? 4,320 watt. The power out of the battery, for the battery now, B equal what? VB for battery multiply I. Okay, volt multiply current. 120 multiply 40. So the answer will be what? 4,800 watt. Okay, this machine is operating as a motor. Okay, converting electrical power to mechanical what? To mechanical power. As you can see also here, B battery, the power here for battery is greater than the power for the shaft or for the rotor here. So it is what here? It is motor, converting electrical what? Power to what? Mechanical power. So this is what here? Motor. Okay, this is what here? Motor. For D, for part D, here will be what? We will repeat the same steps here. Okay, it will be what? A generator. Then E, suppose the machine is running unloaded, what would the final steady state speed of the rotor and the flux density were reduced what to 0.2 Tesla. We'll just solve last part E. Okay, because here for D it will be the same like part C, but it will be what here? Generator. So for E, omega will equal what? E induced over what? 2 RLB. Okay, 120 over what? 2 multiply 0.5 for radius multiply 1 length multiply 0.2 for Tesla, because it is changing now Tesla. So the answer will be what? 600 rad per second. Okay, notice that when the flux in the machine is decreased, so its speed what? Its speed will increase. Its speed will increase. This is the same behavior seen in the linear machine, and the same way that real DC motors behave. Okay, let's go back to our slides. 7.2 commutation in a simple for loop DC machine. Commutation is the process of converting the AC voltages and currents in the rotor of a DC machine to DC voltages and currents at its terminals. A simple for loop 2-pole DC machine is shown in the figure 7.7. Okay, this figure here we have. This machine has 4 complete loops buried in slots curved in the laminated steel of its rotor. The pole faces of the machine are curved to provide a uniform air gap width and to give a uniform flux density everywhere under the faces. This is 2-pole, north and south. Okay, so how many loops we have? 4 loops. Okay, 4 loops. This is a brush, 2 brushes here, A and B. As the number of loops on the rotor increases, the approximation to a perfect DC voltage continue to get better and better. In summary, commutation is the process of switching the loop connection on the rotor of a DC machine, just as the voltage in the loop switches polarity, in order to maintain on an essentially constant DC output voltage. The commutator segments in real machines are typically made of copper bars. The brushes are made of a mixture containing graphite, so that they cause very little friction as they rub over the rotating commutator segments. Section 7.3 Commutation and armature construction in real DC machines. In real DC machines, there are several ways in which the loops on the rotor, also called the armature, rotor it's mean what? Armature, okay, can be connected to its commutator segments, regardless of the way in which the windings are connected to the commutator segments. Most of the rotor windings themselves consist of a diamond-shaped performed coils which are inserted into the armature slots as a unit. The number of conductors on a machine's armature is given by what here? This is the equations. Z equal 2C NC. What is Z here? Z, number of conductors of the rotor. C, number of the coils on the rotor. NC, number of turns per coil. Okay, this is the here diamond shape of the coil. Connection to the commutator segments. Once the windings are insulated in the rotor slots, they must be connected to the commutator segments. There are a number of ways in which these connections can be made, and the different winding arrangements which result have different advantages and disadvantages. The distance in number of segments between the commutator segments to which the two ends of a coil are connected in is called what? It's called the commutator pitch YC. Okay. If the ends of a coil or a set number of coils for wave construction is connected to a commutator segment ahead of the one its beginning, is called what? Is connected to the winding is called what? A progressive winding. If the end of coil is connected to a commutator segment behind the one behind the one its beginning is connected to, the winding is called what? A retrogressive winding. If everything else is identical, the direction of rotation of a progressive wound rotor will be opposite to the direction of rotation of a retrogressive wound rotor. This is now figure we have here. Armature windings are classified according to the sequence of their connections to the commutator segments. There are two basic sequence of armature windings connections: lap winding we have, and what? Wave windings. Two types. In addition, there is a third type of winding called what? A frog leg winding, which combines lap and wave windings on a single rotor, both. So this figure here, A, shows a coil and a progressive what? Rotor windings. Okay, as you can see, from C to what? To C plus 1. Next segment. This is what here? Segment. For B, this is a coil and a retrogressive rotor windings. As you can see here, from C, then behind to what here? C plus 1. Okay, the lap winding. Let's talk about now first type, lap winding. The simplest type of winding construction used in modern DC machines is the simplex series or lap windings. A simplex lap winding is a what? A rotor winding consisting of coils containing one or more turns of wire, with the two ends of each coil coming out at adjacent commutator segments. Since each set of windings has as many current paths as the machine has poles, there are twice as many current paths as the machine has poles in a duplex lap windings. This is some equations for what? For lap windings here. Y is equal plus minus m, and the number of current of the current paths in the machine is given by what? A equal m multiply number of poles, where A number of currents paths in the rotor, m plex of the windings 1 2 3, p number of poles of the machines. Okay, this is a simple two pole lap winding DC machine. This figure here 8.14. okay, lap windings. This is north, this is south. Okay, as you can see from the shape here, this is for example coil 1. okay, then what? Coil 2, coil 3, then 4, 5, 6, 7, this is 8. We have two brushes here, 1 2. okay, and this is also here, this is another figure for what? For lap winding. Wave winding, the series or wave winding is an alternative way to connect the rotor coils to the commutator segment. And in this simplex wave winding, every other rotor coil connects back to a commutator segment adjacent to the beginning of the first coil. Therefore, there are two coils in series between the adjacent commutator segments. The general expression for commutator pitch in any simplex wave winding is what here? This is we have equations. Okay, y c equal what? 2 multiply c plus minus 1 over number of poles. and A will be what here? A equal what? 2m multiplex wave. The last type here, four-leg winding or self-equalizing winding, gets its name from the shape of its coil. It consists of a lap winding and wave winding, both. Okay, both. This is here lap winding, and this is what wave windings. Okay, this is what a symbol for pole wave wound DC machine. 4 poles here: north, south, north, south. We have here 4 poles. Okay, section 7.6, the construction of DC machines. The physical structure of the machine consists of 2 parts: stator and what here? And stator or stationary part, and the rotor or rotating part. The stationary part of the machine consists of the frame, which provides, you have to know each part, okay, and its function, which provides physical support, and the pole pieces which project inward and provide a path for magnetic flux in the machine. The ends of pole pieces that are near to the rotor spread out over the rotor surface to distribute its flux evenly over the rotor surfaces. This is the figure here with the basic here parts of the DC machines. As you can see, we have a yoke, okay, yoke, and what here? Nameplate. This is armature, commutator. Okay, this is the frame. This is the end pill. This is the field pole and field core. This is the brushes. Okay, so you have to know each part and its here function. So yoke, the outer frame of DC machine is called what? Yoke. It is what here? It is made up of cast iron or steel. Okay. So to provide what? Mechanical strength of to the whole assembly. So poles and pole shoes. Poles are joined to the yoke with the help of bolts or welding. They carry field winding, and pole shoes are fastened to them. Okay. So field winding, they are what? Usually made of copper. Okay. Field coils are former wound and placed on each pole, and what are connected in series. They are wound in such a way that when energized they form alternate north and south poles. Armature core here, armature core is the rotor of a DC machine. It is what? Cylindrical in shape with slots to carry what? Armature winding. Armature winding, it is usually a former wound copper coil which resets in armature slots. The armature conductor are what? Insulated from each other and also from the armature core. Okay, commutator and the brushes here. Also here you can see this figure here. Show you the parts of DC machine. This is also another figure here. Okay, field winding, pole, armature, commutator, brushes. Okay, you have to know each part, guys. So here commutator and the brushes, physical connections to the armature winding is made through a commutator brush arrangement. the function of commutator here, okay, in a DC generator is to what? Collect the current generated in armature conductors, whereas in a case of a DC motor, commutator helps to in providing current to the armature conductors. Okay, so also here they reset on commutator segments and slide. So brushes are what usually made from carbon or graphite. They reset on a commutator segments and slide on the segments when the commutator rotates, keeping the physical contact to collect or supply the current. They can carry or they carry the current. Okay, so this is the end here of chapter 7. We have here problems you have to try to solve. 7.1, okay, 7.2, okay, 7.2. Then here we have, okay, 7.4, 7.5, 7.10. Just try to solve, and then I will send you the right solution. Thank you.